So at this point, you can really work all these problems on your own. You shouldn't really even need videos for this section. Um, so the videos are mostly going to be me giving you kind of tips to solve these problems that are going to save you time and make it easier. Okay, you've already talked about much more complicated concepts in projectile motion at this point. So everything we do here is just going to be an application of things that we've talked about before. But I'm just going to give you a couple little tips that are going to help you work problems a little bit easier. Okay, so let's say we have some we know some initial velocity or some combination of parameters, and we need to find the time that something happens in. Okay, so if we need to find the time, then we look back at the previous video, and there are only a few equations that have time in them. Right? One of them is we noticed that we had the velocity in the y direction, and that's the initial velocity of y minus gt. We had an equation in the x direction. X is x0 plus v0x times t. And then we also had a term for y, the y components, y0 plus v0yt plus minus 1/2 gt squared. Okay, so first we're going to talk about this part. So notice that we have three equations. One equation is linear in t. So the Vy equation is linear in t, the x equation is linear in t. Okay? But notice that the y equation is quadratic in t. There's a squared term. Right? So because of that, don't use this unless you have to. So there will be some occasions when, because of the variables given, because of what you're trying to solve for, you might have to use this equation. But do your very best to not have to use it, because it's just going to complicate things, right? It's going to be much more difficult. So for example, let's look at if we want to find out, if we call this the position of the particle A. Okay? So let's look at the things that we know about the particle when it's at A. Okay? It's going to have some velocity, but notice that its velocity is all in the x direction. Right? Conservation of momentum tells us that the x direction of its velocity isn't going to change at all, so it's always going to be continuing in that same direction, at that same velocity. But there's no y component, so Vy is equal to 0 here. So that means when we're at position A, this tells us that 0 is equal to v0y minus gt. And of course v0y is just v0 sine theta. So in other words, the time it takes to get from, if we call this t equals 0, then the time to get from when we launched it to get to point A is just v0 sine theta divided by g. Okay? Then at the end, let's say we want to get to a final point B just before it hits the ground, and we want to find out the time there. Well, similarly, we can say, well, at B, we know that now the velocity y, Vy, is equal to minus v. And the way that we know that, without having to go into too much details, we just think about conservation of energy, right? So initially, minus v0y, right? So the reason we know that is because conservation of energy tells us that initially we had kinetic energy 1/2 m v0 squared, At A, that became mgh. That was the energy at the top. Down at the bottom, we have no kinetic energy again, so it has to have velocity 1/2 m, it had kinetic energy 1/2 mv0 squared. So in other words, the velocity here is going to have the same exact magnitude as the velocity when we initially launched it. But now, of course, our v final is going to be, it still has the same x component, but its y component is reversed. Right? So we know that vy is minus v0 initial y when we get to the end. So what this tells us for b is that minus v0y equals v0y minus gt. So we see that the time at b is going to be equal to 2 v0 sine theta over g. And again, this makes sense because we would expect that if the time to go up was v0 sine theta, then the time to go down would be twice the time to go up. And so that makes sense intuitively. Okay? Now we could have tried to solve this using the height equation, right? Because we can find the height using conservation of energy, because we know 1/2 mv squared is equal to mgh. And then we could have plugged h into y, but then we'd get a quadratic equation for t. And even though we would get the same answer, we would get the same exact answer, but if we did that, we have to go through a much more difficult process to find it, whereas here we just had to solve a simple equation. Okay? But now let's look at what this tells us about the distance that this has traveled. Okay? So we often call this distance in the x direction, we'll label it with r, we often call it the range. And to see how we find the range, we look at our x equation of motion. So we say that x is equal to x0 plus v0 xt. And again, there's no acceleration in the x direction. Conservation of momentum tells us that it's just going to be the velocity of the x component is going to be constant. So this is x0 plus v0 cosine theta times t, which is v0 sine theta, 2v0 sine theta over g. So in other words, x minus x0, if we call x0 this initial point here, is going to equal the range, which is going to be 2v0 squared sine theta cosine theta over g. Okay? And so this tells us the distance. This is the equation for how far we're going to travel. And then, one good problem to work out. I've had a lot of people tell me that they know that if we make theta equal to 45 degrees, that's the maximum angle. That angle will give us the maximum range. And so one thing for you to work out on your own may be to figure out why that is. And so I'll just give you, I'll kind of outline the problem for you and let you do it on your own. But we know that if r is a function of theta, so for a given velocity and a given acceleration due to gravity, so on Earth, for example, then we know what the range is going to be based on an angle theta. And we know if we take the derivative dr d theta and set that equal to 0, this is going to give us a minimum or a maximum. And so if we do that, we can take the derivative here and we can find kind of the maximum value of r as a function of theta. And we can take a second derivative to make sure we have the maximum and not the minimum. And the other piece of useful mathematics to know is you may get to a point where you need to use the fact that sine theta, cosine theta, it's either 2 or 1/2 sine 2 theta. I can't remember if this is a 1/2 or if it's a 2. It's one or the other. But you can look that up on Google to get that. And then that'll show you why 45 degrees has to be the maximum angle to, you know, the angle to get the maximum range.